So we're looking at the kinematics booklet here, the front page, the questions. I think they go to number, is it 16 or something? And then we're going to do the last two example questions today, and then I'll give you whatever time is left. So do some work, do some problems.
Were we supposed to do that first page? Is that what you wanted us
Yeah.
to do? Because I did all the ones after it.
Oh, I wanted the questions done, not the problems.
Oh, and some of the questions and some of the problems.
I wanted the questions done.
That's number 18. I got it for 10.
Number 1, does a car speedometer measure speed, velocity, or both? Just the speed. That's why it's called a speedometer. It's not a velocimeter. Just the speed. You'd need the compass as well to measure velocity. If an accurate speedometer registers a constant value for a period of time, can you determine the average velocity over that period of time using only the speedometer? Why not, David? You need the more specifically the direction. You need the direction as well, right?
What if you put yes as long as it travels in a straight line?
I would accept that, yeah. But you have to have the as long as you travel in a straight line. Number 3, can the average velocity of a particle be 0 over a given time interval if it's not 0 over a shorter period of time? Can you end up with an overall average of 0 if it's not 0 over a shorter period of time? Yes. Give me an example. In what regard? Okay, a roller coaster goes back to the start. Okay, so you're saying it goes up and down all the way around and ends up right back where it started? Good. Okay. As long as the overall displacement is 0, then the average velocity would be 0. And clearly, roller coasters have a velocity greater than 0 at some point, right? So yes, that's a good example. Number 4, can an object have varying velocity if its speed is constant? If yes, give an example. Like something going in a circle, right? Yeah. Okay, or the old rubber stopper on the string, right? Round and around, right? The speed could be constant, but the velocity would be changing because the direction is changing. Can an object have varying speed if its velocity is constant? No, that's not possible, right? If the velocity is constant, that means that it's going in a straight line at a constant speed. Number 6, when an object moves with constant velocity, does its average velocity during any time interval differ from its instantaneous velocity at any instant? They would have to be the same, wouldn't they? Okay, constant velocity means that it's always the same. So all the instantaneous velocities would have to be the same, which would give you the same average. Number 7, can the velocity of an object be 0 at the same instant its acceleration is not 0? Give an example. Oh, this one's a little harder. Can the velocity of an object be 0 at the same instant its acceleration is not 0? Give me an example there, Evan. Anybody else say yes? David? Slowing down to a stop. So you're talking about the instant that it's actually reached stopped. You know, I'm not 100% sure about that. Because I was thinking more about something like this. They're not talking about displacement here. They're talking about velocity. I was thinking more, David, about something going up and coming down, right? Because at this point right here, the velocity is 0, right? Because it's not going up or going down. But the acceleration is minus 9.8 due to gravity. You're just talking about that part up to there, right? So I guess, yeah, that would have to be true, right? Because it's not like the acceleration's turned off for that. So yeah, I guess, yeah. You remember when we did the up-down with the dynamics track here, kinematics track, right? And the velocity, I think, went something like that, right? There was at some point right there where it was exactly 0, but if I graph the acceleration, it was like that, right? Okay. What number was that? Number 7? Number 8, if a car has a greater maximum speed than another, does it mean that it also has a greater acceleration? So is that a yes or a no? Yes? If a car has a greater maximum speed than another, doesn't mean that it also has a greater acceleration. Not necessarily, right? Not necessarily. Possibly, but not necessarily, right? You can have cars that accelerate very fast, but just don't go very fast, right? Like you think of about a little subcompact type of thing. It can get up to speed very fast, but not maybe go faster than say 120 or something, right? Number 9, compare the acceleration of a motorcycle that accelerates from 80 to 90 with the acceleration of a bicycle that accelerates from rest to 10 in the same time. Well, if you're going from 80 to 90 or from 0 to 10 in the same amount of time, those would have the same accelerations, right, Brent? Same accelerations. Can you conclude that a car is not accelerating if its speedometer indicates a steady 60 kilometers an hour? Not accelerating. Could it be accelerating if the speedometer indicates a steady 60? I would agree, right? If you're going on cruise control and you're going around a curve, right, you're changing the direction, so there would be some acceleration. Yep. All sort of the same idea, right, about that changing direction thing. Can an object have a northward velocity and a southward acceleration? Pretty easily, right? All you'd have to do is be driving north and slowing down. Driving north and slowing down. Can the velocity of an object be negative when its acceleration is positive? Right here, right? Can the velocity of an object be negative when the acceleration is positive? What about vice versa? Absolutely, right? Just be slowing down in one direction or slowing down in the opposite direction. Is that number 12? Number 13, give an example where both velocity and acceleration are negative. Pardon me? Speeding up in reverse, Levi, that's correct. Or simply just a ball falling off a roof or something or other, right? The velocity there is negative, the acceleration is also negative. Both down. A rock is thrown vertically upward with a speed v from the edge of a cliff. A second rock is thrown vertically downward with the same initial speed. Which rock has a greater speed when it reaches the bottom of the cliff? Ignore air resistance. Okay, so here's my cliff. Ball number 1 is tossed straight up at, we'll say, 10 meters per second. And ball number 2 is thrown down at minus 10 meters per second. When they both hit down here, which one's going faster? Same, Jeremy? Why do you say the same? Yeah, right there, right? It's going at minus 10. Absolutely. So they're both actually going to be the same at the bottom. Very good. Okay. Which one would land first? The red one? Why the red one? It's got a head start, doesn't it, right? If they're thrown at the same instant, this one, the red one's like down here by the time the black one gets to there, right? They're both going to land at the same speed, but they're both going to land at different times. Okay, number 15. A ball thrown vertically upward returns to the thrower's hand. Which part of the journey requires the longer time, the upward or the downward? Answer A, for no air resistance, and B, in the presence of air resistance. Hint, the acceleration due to air resistance is always in the direction opposite to motion. Now, here's where it gets a little more challenging. Okay? So here's a guy. With no neck. And he throws the ball up, and it returns to his hand. Which journey requires a longer time, upward or downward, if there's no air resistance? For no air resistance, they would clearly be the same, right? The time up is equal to the time down. The initial velocity is the same, the acceleration is the same, everything is the same, right? Everything's the same. But what about when there is air resistance? What do you think? Why the downward? Well, let's draw a couple free body diagrams here. On the way up, okay, on the way up, which way is the acceleration due to gravity? Gravity is the ball's going up, gravity's pulling it down, right?
Yes, and then when it's going down, right, faster.
Well, hold on. Which way's the air resistance? Which way's the air resistance here? Down, right? Air resistance, I'll say acceleration due to resistance, right? Okay, now on the way down, the ball's going down, right? Which way is the gravity? Down again. Which way is the air resistance? It's up. Okay, it's going to be up, right? So which one's going to have this value here, right? If you add those vectors together, is going to give you a overall acceleration of longer than minus 9.8, right? Down. Whereas here it's going to be a little bit less, isn't it? It's going to be less. Okay? So which one's going to have the greater acceleration? Well, yeah, throwing the ball up, right? So which one's going to take longer? Down. Down's going to take longer because it's not going to. Not going to what? It's not going to speed up as fast, right? It's not going to speed up as
So
fast.
it takes more to get it up first, right? Than, like, the speed to get it up, to throw it up, would be greater than going down, right?
I think so, yeah. Air resistance does come into play. And it depends on the size of the object and everything, right? For the most part, we'll say that they're the same. Number 16, an object that is thrown vertically upward will return to its original position with the same speed as it had initially, if air resistance is negligible. If air resistance is appreciable, will this result be altered, and if so, how? Okay, so we're talking about the same thing, right? Is it going to be slower on the way down? That's right. Okay, it's going to be slower on the way down. Okay? Has anyone seen the Mythbusters episode where they fire the bullet straight up and it comes back down and they're trying to determine? It comes down quite a bit slower, I think, from what I remember. Number 17, describe in words the motion plotted in figure 1 below. Okay, so this is a position time graph. And it sort of looks like this, straight. Something like that, right? I probably have these somewhere. This is a position time graph. So describe it in words. Well, you'd say something like, for the first 20 seconds, it's traveling at a constant speed. Then it does what, Jeremy? Speeds up until about 30 seconds, still traveling to the right. Then it begins to slow down, and it reverses direction at approximately 37 seconds. Then it speeds up backwards to about 45 seconds, and then just begins to slow down a little bit up to 50 seconds. And of course, I'm recording this for your listening enjoyment later. The next one is a velocity time graph. Oh, let's just go back to 17. Does that one ever go backwards? 17? Does the object ever go backwards in 17? When does it go backwards? Right there, right? That entire time right there is going backwards, okay? The next one is a velocity time graph. Something like that. Does this one ever go backwards? Julie, does this one ever go backwards? No? How come? Doesn't go below the line, right? Doesn't go below the line. So the velocity is always positive. So what's happening right here? Speeding up at a constant rate? How straight is that line? Not that straight, but not that curvy, right? So it's almost at a constant acceleration. Speeding up at about 50 seconds it begins to slow down, right? It slows down at a almost constant rate. That's a fairly straight line. Once you get down to 90 seconds, the object is stopped, because it's right at 0. So it's stopped until about 105, and then at about 105 seconds it speeds up for the remainder of the trip.